Okay, hello and welcome on another video on applied electronics. So today I'll be solving quiz 1 for chemical engineering students. So that is CH1C2 group A, right? Okay. So let's get straight to the questions. Now, if we look at the questions, we are given question 1 up to question 3. So for question 1 here, you are asked to state 4 properties of an insulator, right? So if you have an insulator, what are the 4 properties? So I'm not going to really write the 4 properties, so I'll just state them. Okay. So when we talk about 4 properties of an insulator, you can think about insulator. If you have an insulator, we know that it's going to prevent the flow of current through it. Then the second property is that for an insulator, the resistivity tends to decrease with an increase in temperature. So if you are increasing the temperature of an insulator, it means that the resistivity of that insulator is going to reduce. Okay. Now, another property, which is that for insulators, we tend to have a very large energy gap between the valence band and the conduction band. All right, so we have a very huge energy band between these two bands that I've just stated. So as a result of that, a lot of energy is needed to move an electron from the valence band to the conduction band, where chemical reaction can take place. Now the last property is that for insulators, so when it comes to insulators, they tend to have their valence band, they tend to have a lot of electrons in their valence band, which make it hard for them to actually lose these electrons as compared to, let's say, as compared to a conductor or a semiconductor, right? So these are some of the properties, but there are a lot of them. These are for the emitter. So there are a lot that you can actually come out with. Okay. Now let's go to B, right? We go to 1B. With the aid of diagram, explain forward biasing. Now when it comes to forward biasing, we know that in order for forward biasing to take place, you have to satisfy some 2 important conditions or requirements. The first one is that you make sure that the bias voltage or the voltage source is greater than the barrier potential of the diode. So each diode that you are going to have is going to have a barrier potential. So you make sure that the voltage source or bias voltage is greater than that barrier potential. That's one requirement. And the second requirement is that you make sure the positive terminal of the bias voltage is connected to the P region of the diode, and then the negative terminal of the bias voltage is also connected to the N region. That's the cathode. Yes, that's the cathode, right? So with this condition being met, then what is going to happen is that because the P region of the diode or the anode of the diode consists of majority holes, right? So what is going to happen is that the electrons, which are majority in the cathode, will now try to force their way to the positive terminal of the bias voltage because of what the force of attraction that is taking place, because the N region has majority electrons which are negatively charged, and then if you look at the positive terminal of the bias voltage, we have positive charges there. So the attraction between these unlike charges is going to cause the electrons in the N region to diffuse into the P region, where they can combine with holes, and then some of these electrons are going to find their way, right? Because as they move into the P region, they tend to lose some energy because of the overcoming the barrier potential of the diode. So the electrons then now tend to be the valence electrons as they are in the P region. Then as they proceed to move to the positive terminal of the bias voltage, you have a wire which is connecting the voltage, the bias voltage, and then the P region. So this wire, or you can call it a metallic conductor that we have there, because they tend to have a secondary, so it has free electrons. So this wire becomes a conduit for the electrons to now move to the positive terminal of the bias voltage. So as a result of the movement of electrons, then you have the flow of current taking place as well. And when it comes to the direction of the flow of current, is always opposite to the movement of electrons. So if the electrons are moving, let's say from right to left, meaning the electrons are moving from left to right, it means the pulse movement, which is indicating the movement of current, also move from left to right in that case. So that's how the forward biasing takes place. Okay, now moving to the next question, which is question 2. So there you were asked to define doping, right? What do we mean by doping? So when it comes to doping is just a process of adding impurities to a semiconductor, right? So if you have a semiconductor, for example, silicon or germanium, and you add some impurities to it in order to enhance the conductivity of the semiconductor, we refer to that as doping, right? So that's doping. It's similar to competitive sports, whereby athletes would take some drugs or some steroids to increase their performance. So the same thing here, the semiconductor, you are adding these impurities so that it can increase the ability of that semiconductor to conduct current. Now let's talk about 2b. Explain the two types of semiconductors. So we tend to have two types of semiconductors. One is intrinsic semiconductor, right? Semiconductors. For intrinsic semiconductors, we are refer to them as pure semiconductors, or semiconductors in their true nature, right? So meaning the semiconductors that we can find in nature, we refer to them as intrinsic semiconductors. So meaning they don't have any impurities, we haven't added anything to them. So we refer to them as intrinsic semiconductor, right? Now, the second type of semiconductors that we have is extrinsic semiconductors. So when it comes to extrinsic semiconductors, they are semiconductors that we tend to have by adding impurities to a pure semiconductor, right? So let's say you have silicon, then you add impurities to it, then that becomes now an extrinsic semiconductor, right? Extrinsic semiconductor. So when it comes to the impurities that we can add to a semiconductor, we have p-type impurities and n-type impurities. So if you take a semiconductor, then you add p-type impurities to it, that becomes what? P-type semiconductor. Likewise, if you are adding n-type impurities to a semiconductor, we refer to that semiconductor now as n-type semiconductor. Okay. Now let's go to question 3. So question 3, we have some calculations there, so I'll try and do the calculation. So we have some calculations here. Okay. So question 3, what is the type of transistor in figure 1? So you can see here figure 1, we have this circuit diagram. We are trying to look at the transistor that we have here. You can see we have a transistor here. This is a transistor that we have here. So we are asked to find what is the type of transistor. So you can see this is what a bipolar junction transistor. So under bipolar junction transistors, we have what? We have n-type, NPN, and then PNP, right? So if you look here, how do we know the kind of the type of bipolar junction transistor that we have in this circuit diagram? By looking at the flow of current that is indicated here. So you can see that the current is what? Leaving the base. So as a result of this, this is going to be considered as NPN. So we have NPN bipolar. This is 3A junction transistor. Okay. So this is for 3A. Now moving to 3B, calculate IB, IC, and then IE. Assume VBE equals to 0.7 volts. Now looking at this circuit diagram, we have to find IB. IB here is the base current. So to find IB, for example, we try and look at the circuit diagram. We can see that we have voltage source 10 volts. And then we have 470 kilo ohms, and then we have here from there it goes to what? Ground. So you can see here we can get a closed loop here or a closed circuit. So we have this as a closed circuit. Now with this closed circuit, what we are going to do that we are going to apply Kirchhoff voltage law to this closed circuit, which is just a loop, right? So I'm going to indicate as even loop 1. So we are applying Kirchhoff, this is 3B, Kirchhoff voltage law to loop 1. Okay. Now with this, so applying Kirchhoff voltage law to loop 1, we can see that if we are moving clockwise, so I can have 10, which is a voltage source there, 10, which is rise. Then we have a resistor, so that resistor is going to be dropped. So the voltage across the resistor is going to drop. So we have minus, so the voltage across the resistor here will be the current which is passing through it. And that current we can see, we label the current as IB. See, that current is entering the base, right? So as we refer to that current as the base current. So IB is here. So that means the voltage across the RB, which is meaning the base resistor there, is going to be equals to the current which is passing through that resistor. So that will be what? IB times that resistance there, which is RB, right? So we have here to be 470 kilo ohms times what? The base current, which is IB, again minus. So this time we can see that we are given VBE. We have VBE here, and which is 0.7. So when we are moving clockwise, we have what we refer to as the base emitter voltage. So that one is here. So this is our VBE, this part. So that place is going to be dropped. So as a result of that, meaning we come in here minus VBE, that is equals to 0. So this is the equation that we get. You can see VB, like we just said, is what, 0.7 volts. So we replace it here and then make the base current the subject. So IB is going to be equals to 10 minus, now VB is 0.7 volts over 470 kilo ohms. So meaning I'm going to take 9 minus 10 rather, this is the voltage of this 10 minus 0.7, then here this comes up, so we get 10 to the power minus 3, meaning this divided by 470, that gives me 0.01. Okay, let me erase this so that I can write it very well. So the answer I'll get here is 0.1979. Okay, now times 10 to the power minus 3. So this here IB will be equals to, we change this into, we already have 10 raised power minus 3 here, so we can change this to have another 10 raised power minus 3, so that we get here will be, we move 1 2 3, so I'll get 19.79 times 10 to the power minus 3 times another 10 to the power minus 3, that will now be equals to 19.79 microamps. Okay, so that's for IB. So we move to the next one, which is IC. IC, we can calculate IC. If you look here, we have what, beta DC, which that is the gain, the DC gain there. We have beta DC is equals to, is going to equals to the output, which is IC, over the input here, which is IB. So we make IC the subject, which is going to be equals to beta DC times IB. So we have this to be equals to beta DC, you can see here is given from here as 200. So that means I have 200 here times, so I can write here 19.79 times 10 to the power minus 6. So we take this times 200, so we get 3.9. okay, so 3.996 milliamps. Okay, so we get 3.96 milliamps. So that is the collector current. Now let's with IE, which is the emitter current. Emitter current, we know is going to equal to what? The sum of the base current and then the collector current. So we are going to have base currents being 19.79 times 10 to the power minus 3 plus 3.96 times 10 to the power minus 3. Okay, so that means what do I get for this? Meaning here, what I can do is that, okay, let me just do all of it straightforward, times 10 raised to the power minus 3. Okay, so we get this plus 199.79 times 10 raised to the power minus 6, right? So you can see here we end up getting 3.98 milliamps. Okay, so this becomes our answers for this. So this is what we get for as our answers, and then we have this. Okay, so we've come to the end of this video. See you on the next video. Bye bye.